everyone. So today we're going to be talking about making and understanding linear approximations. So basically, the first part to understanding a linear approximation and what it is and how you can make one is understanding why they exist and why they're relevant. So if you read here, because ordinary functions are locally linear, that means straight, and the further you zoom in on them, the straighter they look. A line tangent to a function, if this is the function here, this curved line. A line tangent to a function is a good approximation of the function near the point of tangency. So this basically means if you take this function, and then you take the tangent line tangent to the function, which would be this line right here. I'm not going to draw on that just so you don't get confused. That tangent line is an approximation of the value of this point wherever they cross, near the point of tangency. It's an approximation of the function near the point of tangency. So you are approximating the value linearly of the function. So as modeled up here, so this is the graph of y equals, just so you can see it better, y equals x, or y equals root x. And the tangent line meets this function at 9, 3. So as it says here, you can see that near 9, 3, the curve and the tangent line are virtually indistinguishable. So because they meet at that point, and the closer you zoom in, the straighter they look, it seems as if these functions actually line up. So, therefore, you can approximate, because they're virtually indistinguishable, that's an important word, virtually. You can approximate, linear approximation, the equation of the tangent line at 9, 3. So, doing so requires taking the derivative of the function. So if, I'm just going to write this all out over here so you can see it better. If f of x equals root x, or x to the 1/2, f prime of x, 1/2 x to the negative 1/2, or 1 over 2 root x. So that's the slope, because we know what derivatives are. The derivative of f of x is the slope of f of x at any given point. So, in order to find the equation of the tangent line at 9, 3, you're going to find the slope of the function at 9, 3. So, f of 9 equals 1 over 2 root x, or x is, in this case, 3, or y in this case is 3. I'm sorry, 9. So you plug in 9 for x, and you get 1 over 2 root 9, which is 1 over 2 times 3, or 1 over 6. So, again, this isn't an equation, obviously, but this is a derivative, which makes it a slope. So this 1 over 6 is the slope of both, because they're virtually indistinguishable at the point, it's the slope of both the function and the tangent line. So if we know that this is the slope of the tangent line, and it's at 0.93, you can plug them in point slope form, which is right here. I'll rewrite this. So in this case, y minus 3 equals 1 over 6 times quantity of x minus 9, or y equals 3 plus. Just simplifying. So typically, just for simplification's sake, because obviously going from point slope form into the simplified form isn't calculus, you could just leave it as this form right here, and there you have the equation of your tangent line. So again, it's just important to think back and understand why we're doing this and why this is the slope of the tangent line at this point. It's because the tangent line, because they meet and they are virtually indistinguishable, it's a good approximation of the function, and vice versa. So if you were to plug in 9 here for x, you would get 3. So you know, just by checking your work, you know that this is true. So let's read on. So this is the equation of the line tangent to the function f of x equals root x at 9, 3. You may be wondering why it's written in point slope form. It might seem more natural to put the 3 to the right, which of course would be correct, and you could simplify it further, writing it in slope intercept. Zoom in on the point 9, 3 a couple times, and you see that the curve gets straighter and straighter, and the curve and tangent line get closer and closer. So let's read on. Now, say you want to approximate the square root of 10. Because 10 is pretty close to 9, and you can see from the figure that f of x and its tangent line are close to each other at x equals 10, the y-coordinate of the line at x equals 10, the tangent line, is a good approximation of the function value at x equals 10, the function being y equals root x. So we have some scribbles over here. Namely, root 10. So again, this is an approximation. So you're using, so because you used your function to find the derivative of the function, to find the slope of the tangent line to the function, and then you plugged in your point, which was 9, 3, to find the equation of the tangent line. And now that you have the equation of the tangent line, you're using that equation to find approximations, that's the important thing to remember, approximations of the function. So essentially, this whole lesson just focuses on the ability of using a point and a tangent line to approximate points of a function when you don't have points of a function in just a simpler way. So plug a 10 into the line equation for your approximation. So if y equals 3 plus 1 over 6 x minus 9, or (10 minus 9). You can simplify that, turns down to 1. 1 over 6 times 1 is 1 over 6. So this is just a simple way. If you don't have a calculator, or if you're on a no calculator portion of a test and you need to know what is the value, sorry, we're flipping back really quick, what's the value of y equals root x at 10, and then this is your variable. You can't, unless you have your square roots memorized, you don't know what the exact square root of 10 is. So an easy way to do that is you have your point, you have your function, you know you can approximate linearly. So here, let's read on. So the square root of 10 is 3 1/6, or 19/6. And the exact answer is 3.1623. And this is about 3.2, or 3.12. So let's read on. So this error is roughly 0.1%. So that's a great way to approximate values and get answers for something that you couldn't really do without a calculator, which I couldn't do root 10 without a calculator. So let's explain why we leave it in point slope form. So this form makes it easier to do the computation and to understand what's going on when you compute a linear approximation. So you know each step of the way where you're plugging in each value and what the significance of the 9 is, what the significance of the 3 is. So you know the tangent line goes through 9, 3, and you know that the slope of the line is 1/6, which we computed earlier. So you can start at 9, 3 and go to the right or left along the line in the stair-step fashion, as shown in the figure below. So basically it's just leaving it in the point slope form is a benefit of you can easily plug in 7, 8, 9, 10, 11, 12 and get a simple answer. You multiply it by 1, you divide it by 6 and add 3. Divide 11 by 6, add 3. Divide 12 by 6, add 3. So when you're doing an approximation, you start at a y value of 3. And go up 1/6 for each 1 you go to the right. So or if you go to the left, you go down 1/6 for each 1 you go to the left. When the line equation is written in the above form, this one right here, if you can't read that, it's when the line is written in the above form, right here, the computation of a linear approximation parallels this stair-step scheme. This figure shows the approximation values for the square roots of 7, 8, 10, 11, and 12. Here's how you come up with these values. So this is just a way to kind of visualize, if you're a visual learner, what this equation really means and why we use this as opposed to this form here. Because this definitely makes it more complicated by adding fractions and you have to multiply, So, if you're a visual learner, you need 8. So you go 1 to the left, and down. Down 1/6 from 3. Down 1/6 from 1 to the left of 9 is 8, which is what you need. And 1 down from 1/6, or 1/6 down, from 3 is 2 and 5/6. So that's why leaving it in this form is easy, because you know if your number is 1, 2, 3, etc., values smaller than 9, you go 1, 2, 3 to the left of 9, 8, 7, 6, etc. So, moving on. So now I have work here, but we'll be going over this, so no worries. So again, we just learned how to make linear approximations and what they mean and why they're beneficial. and why we use them on a test or any other form like that. But now we're going to be talking about them in more of in calculus terms. So the equation of a tangent line to a curve at the point A, f of a, which would be right here, is y equals f of a plus f prime of a, or the slope, m, times x minus a. So this can also be written as does that look familiar? That's the form that we were using right here. So since the curve of f of x, or in this case, x or a being a specific point of x, and the tangent line are close to each other for points near x of a, f of x, this is important, is an approximation of f of a plus f prime of a times the quantity of x minus a. So, write an equation of the tangent line to this function at this point. So f of x equals x cubed at 2, 8. So first and foremost, you have to write an equation of the tangent line, and then you have to find the approximate values of f of 1.9 and 2.01. So if we know that f of x equals x cubed, we know that the first step in writing the equation of a tangent line is finding the slope of the tangent line, because we already have x1 and y1, which are visible here. y1, x1. So what we need to find is the slope here, m, or here. So to do that, we can use, because they are virtually indistinguishable, the slopes are virtually indistinguishable at that point. So f prime of x is 3x squared, and f prime of 2 equals 3 times 2 squared, or 12. So then we have x1 and y1, so we can go y minus 8 equals 12 times x minus 2, or y equals 8 plus 12x minus 2, just to keep that in the same form that we're going to be using here. So to approximate, all you do is plug in your x value. So I'm running out of space here, so I'm just going to go right over here. So if we're trying to find f of 1.9, you plug in 8 plus 12. We leave that the same, 8 plus 12 times the quantity of x minus 2. In this case, 1.9 minus 2. So you do that math, 1.9 minus 2 times 12 plus 8 gets you to 6.8. Feel free to plug that into your calculator. Or f of 2.1 is approximately, remember these aren't exact values, and that's what's important to remember, is that we're not trying to find exact values, is we're trying to understand the relationship between linear functions and other types of functions, with tangent lines and other functions. F of 2.1 is approximately y1, or 8, plus m, or 12, or f prime of a, whichever way you'd like to think about it, times 2.1 minus 2, or x minus 2, which ends up being 8.12, 8.12. So your approximations fall at 6.8 and 8.12. If you'd like to do the math, feel free to double check. You can see the approximation of 1.9 cubed or 2.01 cubed, but it should be that they fall right in and around these values here, respectively. So this is going to be a different type of, so this is the same thing that we saw on this worksheet, where we were learning about, we have a point and we have a function and find the equation of the tangent line. And now we're just going to be putting that to use in different forms. So if f is a differentiable function, and f of 2 equals 6. So we know that that's our point. Just going to write this over here, 2, 6. And f prime of 2 is negative 1/2, so we know the f prime of 2 is our slope of our equation line, so we can write that in just to make it a little simpler. Find the approximate value of 2.1. So in this case, they've given us all the information we need. We don't need to find the slope in order to write the equation of the tangent line. We have all the information we need. We have our y1 and we have our x1. And we have our m. So I'm just going to write over here, following along this, same thing. Y minus 6 equals negative 1/2 x minus 2. So f of 2.1 equals 6 minus, not plus because it's negative, 1/2 times 2.1, minus 2. And that is approximately, that's the important thing to remember, is approximately 5.95. So this is it's an interesting case because if you're someone who likes to check your work, this isn't one that you could necessarily plug back in to verify. This is a little different because they didn't give you the equation of the function like they did here. All they gave you was your point and your slope. So this is just kind of learning. You're gonna have to trust just the math here. So this is another different type of example. So if the slope of a function at any point xy is negative x plus 1 over y. So this is function f. This is the slope of any function f. I always like to think about it that way. So if the point 3, 2 is on the graph of f, write an equation of the line tangent to the graph of f at x equals 3. So this one, it's always important to think about, okay, what do I need to get to, and what do I need in order to get there? So first and foremost, you need to write an equation of the tangent line. So you have the formula for the slope, but you don't know what the slope is. So you know that this is another way of writing in, say, an implicit form that the slope of the derivative of f is x plus 1 over y, negative x plus 1 over y, or m, again, because that's slope. So, you know it's 3, 2, so you're trying to find the slope at that point. So f prime of 3, if you like to think about it that way, is negative 3 plus 1 over 2, or negative 2. So if you know that that's your slope, and you know that this is your point, y minus 2 equals 3 minus, because it's negative 2 times x minus 3. Got myself mixed up. Y minus 2 equals negative 2 times x minus 3. So in this case, this is incorrect here. Had some little math errors. Or y equals 2 minus 2x minus 3. So your approximation, you're going to plug in 3.1, which we can do right over here. 2 minus 2 times 3.1 minus 3 ends up being, I'm going to do this on my calculator because I messed up my math the first time. Feel free to follow along. $1.8. And even though you can't necessarily plug answers back in questions like this and like this, you know that if your value at 2 is 6, and your approximated value at 2.1 is 5.95, that's very close. I mean, you know that that's marginal error, and that's likely your correct answer. Same thing here. If you know that your value at your point on your graph is 3.2, and you're approximating 3.1, and you get 1.8, again, marginally close. It's only a difference of 0.2 and 0.05. So it's just important to just kind of remember that even though you can't necessarily check your work, it's easy to tell. If I got 17.95 here, I would know that I had messed up somewhere and would need to go back and check. So we're going to do 2 last examples here. So I don't necessarily have the work to do these, so I'm just going to follow along as I go through. So approximate the value. So this is a trig function. So approximate the value of sine 29. So another way so you have to think about, if I'm approximating sine 29, what's my function likely? My function is probably, if I'm approximating a value of a trig function of a degree, it's likely that trig function is my original function. So f of x is equal to sine x. So then, therefore, you know that in order to approximate, you need to find the tangent line. The equation of the tangent line. And in order to get the equation of the tangent line, you need the slope. So the first thing you're going to do is differentiate. So f prime of x, or f prime of sine x, is cosine x. And you're going to find the slope at, this is where it takes educated guessing. You need to know that you need to think logically here. What's the most likely point of the original function that it would be approximating near? And that's cosine 30, because you know 30 degrees is on your, excuse me, you know 30 degrees is on your unit circle. Stuff like that. Again, unit circle should be memorized, which is why this would be on a no-calc portion. So if you want to go ahead and plug this into your calculator, the exact value of f prime of 30 is 0.87. And you know your original points, because you just plugged them in, are 30 and that's your slope. You know your original value is whatever the sine of 30 is, which in this case is 1/2. So you plug it into your formula. So y equals 1/2 plus root 3 over 2 times the quantity of x minus pi over 6, or 30 degrees. So then the approximate value of 29 is f of 29. F of 29 is approximately 1/2 plus 0.87 times 29 minus 30, which ends up coming out to negative 0.37. So when you get to more problems like these, they're a little more complicated, and you just kind of need to think outside the box and think what's the most likely close function. So same thing here. So if you need to find the approximate value of root 50, you know that whatever you're approximating is, this has to be the x. 50 has to be the x value if you're plugging in an x value on your tangent line, if that makes sense. So you know that x has to be under, so x, in this case 50 is x, so f of x has to be root x if you're plugging in 50. So if you know, therefore deductively you know that f of x is root x, so f prime of x is 1 over 2 root x. So if you're approximating 50, what's the closest square root to 50? That would likely be a close point that you'd be approximating near, or something like that. Again, think no calculator. Is 49, easy root. F of 49 is 1 over 2 times root 49, which is 7. So 1 over 2 times 7 is 1 over 14. So that's your slope. If I'm going through this fast, I apologize. So moving on, you have your slope now at your point, and you have your point, which is 49. Your original point would be 49 and 7 if you were to plug 49 into root x. So, therefore, you know y equals 7 plus 1 over 14 times the quantity of x minus 49. And if you're approximating for 50, you know that f of 50 is equal to 7 plus 1 over 14 times 50 minus 49, or 1. So 7 plus 1 over 14, 99 over 14. So there you have it, guys. That's linear approximation, and that's learning about not only how to make them, but understanding them and why we use them and in the right context. So good luck.